on Bitcoin for software engineers, which I imagine probably everyone is. So it's a bit more technical. So about me, my name is Noah Ruderman, friends with Wen, work at Microsoft, used to work at Facebook if that matters. There are a few ways you can find me, Twitter, LinkedIn, my personal website if you care to. But I don't have any special connection to Bitcoin. I'm just a guy who is very interested in cryptocurrencies and cares to learn a lot about it. So what this presentation covers. When I say this is a presentation for software engineers, the way that I've sort of changed this from how I might normally present it to someone is that I talk about the technical building blocks of Bitcoin first. So I imagine the first part of the presentation, you're just going to be introduced to pieces of it. You might not necessarily intuit at the time how they all sort of fit together, but it'll be easier to understand once you have all of these pieces, how they do fit together, at least from a technical standpoint. And yeah, then I talk about Bitcoin from the user's perspective. So if I just talk about these individual pieces, it's not necessarily clear how sort of the Bitcoin network works as a whole. Then I talk a bit about the use cases for Bitcoin. Like, okay, I've talked about what the system is, but why do people bother even using it? And if there's time, which I think that we probably won't make it, but there are a couple of miscellaneous topics that are kind of interesting, so thought I'd just put it in there. So what is Bitcoin? One way to think of it is a composition of cryptographic technologies to create an entirely new asset. The one interesting thing about Bitcoin is it's very difficult to come up with a single good explanation for what Bitcoin is. It is so radically different from everything that we're already familiar with. It's probably analogous to the birth of the internet in, probably somewhere between 1970 and 1995, where there just weren't really good analogies for explaining what it was. But if I had to give an explanation, at a high level, Bitcoin is an information system for recording and transferring wealth. And this sort of way of looking at Bitcoin is useful in that if Bitcoin were to ever be replaced in the future, it would also be replaced with an information system of some kind. But if we're going to look at Bitcoin from a technical standpoint, we can also think of it as a global, decentralized, append-only database that anyone can write to. This is in stark contrast to databases today where only administrators can write to it or authorize others to write to it. It's sort of a new concept where 7 billion people can write to the Bitcoin blockchain according to the rules of the protocol in any way. So now we're going to jump into the building blocks of Bitcoin. So the first is a concept of a peer-to-peer network, which I imagine you guys are all very familiar with. So in a peer-to-peer network, every node is a client and a server. There's no concept of privileged nodes. So if half of this network were destroyed in a nuclear war, this network would still survive. In fact, only one copy of the Bitcoin blockchain needs to survive anyway. But the health of this network really does depend on a robust set of full nodes. Currently, Bitcoin has about 10,000 reachable full nodes. There are probably many more unreachable ones though. And you can compare this to Tor. So previous to Bitcoin, Tor was sort of the leader in sort of distributed network node count. And Tor has about 6,000 nodes. So the number of inbound and outbound connections is not necessarily particularly important to the protocol, although there are default values for the software that you might run. There are about 10 outbound connections and 115 inbound connections. All these nodes are constantly gossiping towards each other. They're gossiping data, transactions, blocks, etc. And here's a sort of geographic distribution of these around 10,000 full nodes. It's mostly an American and Europe thing, but it really is still global. It's just the density seems to be concentrated in, Western nations for now. So now we're going to talk about public key cryptography. This is pretty foundational to Bitcoin. So public key cryptography is also known as what? Asymmetric? Yeah, asymmetric cryptography. So you have two pieces of data here. public key and a private key. The public key is for everyone in the world. You can share it far and wide. The private key is only for you. Now, what's interesting is that these public and private keys, they actually perform inverse operations on data. If you apply a public or a private key to data, it's going to scramble it. It's going to essentially create something that you might call ciphertext. Let's see if I have an example. So in the middle, that's sort of what ciphertext might look like. On the left is a message. You can invert it with the public or private key, and then you can invert it with the opposite key. Now, how it works is you can perform two operations here. One is encryption. The purpose of this is that only a certain person can receive a message. So for example, if we have Alice and Bob, they each have their own private keys and they distribute their public keys widely. If Alice wants to send a message to Bob that only Bob can read, what she does is she takes Bob's public key, she encrypts the data, and then sends that encrypted data to Bob. Anyone can intercept that data, but it's ciphertext. They can't figure out what the original message is. Once Bob has the ciphertext, he can apply his private key to get the original message back. Now, if you sort of invert these operations a bit, you can get what's called a signature. It's proving ownership of a private key. So for example, if Bob wants to prove that a message came specifically from Bob, all he has to do is take some data and he's going to, he could encrypt it directly with his private key or take a hash of the data and encrypt it. All that matters is he performed this operation with his private key. Then he can send out this data and anyone can take this public key, the corresponding public key, and verify that they get the original message back, which is to say the only person who could have created that ciphertext had the private key. For Bitcoin, the importance is in the signature. It's not actually in encryption. So,
Noah, sorry to interrupt. We have a question in the chat, and the question is, can you go back to the global map slide? And the question is it for the number of accounts for computational power?
This is just number of nodes. So these nodes aren't mining. Bitcoin has two different entities on this network. One are nodes, the other are miners. Just in case you happen to know a bit about Bitcoin beforehand, nodes just keep a copy of the Bitcoin blockchain and they gossip it far and wide. Miners create new blocks, but I haven't really gotten into mining yet. So these are just the nodes. Does that answer your question?
Thanks, yes.
Okay, cool. Okay, so as I mentioned, public key cryptography is important in Bitcoin for signing. Okay, now we're going to talk about the concept of a hash function. I think we're all probably implicitly familiar with this, but I guess we can make it a bit more explicit now. Hash functions are essentially one-way functions. You can think of them as a way to generate a fingerprint from data. So you can have arbitrary data. It could be an image, it could be a string, it could be a movie. And you apply this hash function to it, and you get this fixed length string of data that really should look random. I go to the next slide. These are basically the important properties of hash functions. Need to be easy to compute. It must be very hard to reverse a hash function. So if you have that fixed length, random looking string, it should be very difficult to figure out what piece of data it originally came from. And there's this concept of collisions, which is really just to say that if you were to reverse a hash function, there would only really be one set of data instead of multiple sets of data. So Bitcoin uses a hash function called SHA-256. The output of SHA-256 is 256 bits, so it's 32 bytes. And you can also interpret the value of this hash function as a number between 0 and 2 to the 256 power minus 1. So just below, I give an example of what the SHA-256 hash of Bitcoin looks like, this, garbled string. Okay, so now we're going to talk about the blockchain. This is probably, what people always hear about with Bitcoin. If they hear one thing beyond Bitcoin, it's blockchain. So one way of thinking about blockchain is that it's a clever way of using hashing to tamper-proof data. Now, a blockchain is an append-only data structure. The smallest unit of data that you extend to a blockchain is a block. So you add data in blocks, hence you get a chain of blocks. And the actual blockchain doesn't necessarily need to be a linear chain. It's really a directed acyclic graph. But practically speaking, there's really only meant to be one linear chain that's the authoritative set of blocks. Now, blocks contain a number of, a few pieces of data. I don't think the important part for the blockchain is the hash of the previous block, which is to say every single block is connected to the previous block. And the reason this is important is that each block has an ID. This ID is the hash of all the data in a block. And what this means is that if you have a block that were in some way tampered, that would mean that its hash changes. And if its hash changes, that means that the subsequent block isn't correctly linked to the previous block, which is to say it's actually fairly straightforward to detect if there's any sort of tampering in blocks. And then the one question you might ask is, okay, well, what if we just, construct a, redo the hashing and make sure everything is right after the point that we tamper with it? Well, as long as we make blocks hard to construct, we can make it very hard to tamper with. Okay, here's an example of a chain of just 3 blocks. As I mentioned, for now, just think about the connection to the previous hash. That's the important part that makes blockchain tamper-proof, and I'm going to discuss some other parts at another point. The Merkle root, I'm sort of going to breeze over this. It's not particularly important for understanding how Bitcoin works. So you can just not understand it and your life is going to be the same with your understanding of Bitcoin. But I leave the slide up just in case you want to take a look at it. The brief overview is that Merkle root allows you to include a large number of data in such a way that you can very quickly prove the inclusion of data. There are some Bitcoin nodes that don't actually contain the entirety of data from the Bitcoin blockchain. Instead, they just contain the block headers, which means that they don't contain all the transactions. But what this allows you to do is run a very lightweight Bitcoin blockchain, and you can talk to other nodes on the network and say, can you give me the Merkle root proof for this transaction? So you can be confident that a certain transaction actually existed in the Bitcoin blockchain with a relatively high level of confidence, despite only using a very small amount of data that's not a complete set of data. Proof of work is much more foundational to Bitcoin. I mentioned that blocks need to be hard to produce, and this is generally done through proof of work. Proof of work is very hard to compute, but very easy to verify. So for Bitcoin, the concept of proof of work is that I mentioned these blocks having an ID. Now, it turns out everything in these blocks is generally fixed. I mean, you can adjust the timestamp when you're creating the block, but the important part is this field called the nonce. So when you're ready to construct a block, you essentially put all the data together that's fixed except the nonce. And what you do is you vary the nonce to change the ID of the block until you get an ID that fits certain requirements. And these requirements are related to proof of work. So we know that hash functions are essentially one-way functions, and the only way to find a correct target value is with brute force, because these values are essentially going to be random. So we have this concept of finding a difficult to construct block by choosing a nonce such that the hash of a block has a large number of leading zeros. Now, I mentioned before that SHA-256 has 256 bits, and you can interpret this as a number. And if you look at it that way, then you can sort of think of the concept of a large amount of work, meaning that the hash value, if converted to decimal, is a relatively small number. That's sort of the same thing as having a large number of leading zeros. And the only way to find a nonce such that the block ID hash is very, very low is to brute force it. So if you come to me and you can show me a hash that is just a very, very small number, I can reasonably guess that you put in a lot of work to construct that. And the Bitcoin network right now has about 150 plus exahashes of data. It is incredible how quickly there are advances in computing just for essentially computing these hashes. So here's a quick diagram here. This is a log scale, by the way. So this isn't just like, oh, you know, a slow increase. This is a rapid increase. If it were a linear chart, it would essentially look flat up until maybe around 2019 or so, and then it would go exponential. Okay, so quick overview of this concept of consensus. Bitcoin is a probabilistic solution to the Byzantine generals problem, which I'm guessing you guys are all familiar with. The analog here is that Bitcoin's coordination problem is there are a lot of different blocks out there. I mentioned that the blockchain is actually a directed acyclic graph. However, the whole concept of, there's this concept of which blocks are the correct blocks to include, because the blockchain is intended to be an append-only data structure. It's really meant to be just a linear chain here, at least in Bitcoin's case. So the coordination problem here is which set of blocks are the correct blocks that we want to consider, you know, confirm part of the Bitcoin blockchain that represent transfers and user balances. So all 10,000 Bitcoin nodes, or however many nodes may exist in the future, need to agree on what the correct set of blocks is over an unreliable network where they might not necessarily trust each other. So this process is called consensus, and it is a probabilistic solution to the Byzantine generals problem. So as I mentioned, each block is associated with a certain amount of work based on its hash value. So how the network deals with this is each full node selects the linear set of blocks in this directed acyclic graph of blocks with the most accumulated work. And in that way, the network can probabilistically agree on a single chain of blocks. And you might wonder, why is it probabilistic? So there can sometimes be disputes near the tip of the chain. So for example, you might have a full Bitcoin blockchain and suddenly two blocks are created at the same time. You receive them at the same time. They're from different miners and they're not consistent with each other. So which one is the correct one? Well, according to the rules of the Bitcoin protocol, you're supposed to keep the first block that you receive. And what this might mean is that you have half of the network that has block A and half of the network that has block B, and there's a fork near the tip of the chain. But as time goes on, there's generally a convergence. And this convergence happens very quickly. It usually happens within about 3 blocks, if we're just talking about scenarios where the network is not being attacked and the network's just being honest. So that convergence happens pretty quickly. So Bitcoin doesn't actually provide 100% finality, but rather the finality sort of asymptotically approaches 100%. The likelihood that a block will no longer be included in the Bitcoin blockchain because some sort of fork of the blockchain will somehow be extended faster than the old network and be considered authoritative, the probability of that decreases exponentially with each block. Blocks that are not considered authoritative but pass a validation checks, nodes still keep them. They're called orphan blocks. So here's a quick example of this directed acyclic graph that I'm talking about. The white blocks are orphan blocks. The gray blocks are the main chain. Black is just the genesis block. You have to start somewhere, and genesis block, I think, is hard-coded into the protocol. Okay, now we're going to chat about how Bitcoin works from the perspective of users. So earlier someone asked if the chart that I showed were nodes or miners. So this sort of brought up this concept of these two different kinds of nodes. So I mentioned Bitcoin's a peer-to-peer network, and that peer-to-peer network is for Bitcoin nodes, not Bitcoin miners. Generally, miners are also nodes, but I guess the difference here is that the nodes gossip blocks, transaction data, and keep a copy of the blockchain. Miners run some extra software to mine blocks. So miners are generally also nodes as well. It would be a little bit insane to mine blocks without knowing the actual state of the Bitcoin blockchain. So as I mentioned, Bitcoin nodes, they gossip transactions, they validate blocks, and they don't gossip things that are invalid. So if you have a valid piece of data, it'll generally be propagated to the entire network over a short period of time, probably usually less than a minute. And Bitcoin nodes aren't incentivized. People don't have an economic incentive to run a full node. However, the incentive to run a node comes from client-side validation. So you can be sure that the state of the Bitcoin blockchain is with a high, is accurate, with a high degree of certainty. Compare this to potentially, I don't know, using a Bitcoin block explorer where you're trusting a third party, or possibly using an exchange where you're trusting another third party. So Bitcoin miners, they construct blocks by brute forcing nonces such that the hash of the block has many leading zeros. You can interpret that hash value as a number, and if it's low, that means that there's a lot of work in it. So Bitcoin miners are incentivized. They receive block rewards. When they construct a block, there is something called a Coinbase transaction, which rewards the miner with the Coinbase amount. There's a secondary reward called transaction fees. Transaction fees are actually set by users, and the incentive here is users might want their blocks or their transactions included faster within a block. And if you have more transactions than can possibly fit in the next block, then that means that there's a market for it, there's competition. So Bitcoin is programmable. Bitcoin uses a Turing incomplete language called script. Script is a stack-based programming language. It's kind of like reverse Polish notation. Operators are called opcodes, lots of different kinds. Many kinds are just logged for the sake of security. The main reason Bitcoin isn't Turing complete is for security. So the most popular script is called P2PKH, which is pay to public key hash. It's a sort of compressed way of paying to a public key. So I have an example of this going on here. So on the right, these are the arguments to pay to public key hash. The first two arguments to the script is actually, it should be the signature and then the public key. So when this starts over, about right now, signature and public key are going to be passed on to the stack. We're going to duplicate the public key. Then we're going to take a hash of it. Then we're going to compare it to the public key hash. Is it correct? Good. And then you're going to check the signature. That's it. Fairly simple. So the smallest unit of Bitcoin ownership is called a UTXO. Strictly speaking, the smallest smallest quantity of Bitcoin is called a Satoshi, which is 1 out of 100 million Bitcoin. But Bitcoin are logically grouped into containers, and these containers are called unspent transaction outputs. These unspent transaction outputs naturally contain a numerical quantity of Bitcoin. They also include a redeem script, which is a predicate whose execution needs to evaluate to true for the coins to be spent. So this is where Bitcoin's programmability comes from. You can program it in various ways beyond just paying to a public key hash. In fact, it doesn't even need to involve public keys, but if it didn't, you might have some sort of issues with front running, where, for example, you might say you can unlock this transaction if you find a hash or a value that hashes to this special value. And what happens is you might send a transaction to the blockchain. You say, well, actually, it's the string Bitcoin that hashes to that. Someone else who's monitoring the mempool, or essentially the network of transactions which haven't made it into a block, might take that data, create a new transaction with a higher transaction fee to front run you. But regardless, there are actually many ways that you can program Bitcoin's redeem script. It just usually involves public and private keys in some way. So Bitcoin does not use the account model. The account model is address A has balance B. Instead, Bitcoin's model is the UTXO model. It's UTXO A has redeem script B. So UTXOs collectively form the global state of Bitcoin. You can very easily validate all the Bitcoins that have ever been created on your full node in a fraction of a second. This is actually not possible with gold, and also not possible with national currencies.
Hey, Noah, I have a question in the chat.
Yeah.
Zhen is asking, how do miners determine which information to wrap into a block? Maybe deceptive transactions can be wrapped into a trustworthy miner's block?
Well, the first is that miners will validate transactions. So at the very least, they won't be including transactions that cause their block to be rejected. And assuming that transactions are all valid, miners are economically incentivized to include transactions with the highest transaction fees. So it's actually entirely up to the miner. It's possible a block can be mined without any transactions, and that sometimes happens when a block is mined extremely fast. So for example, maybe a miner constructs a block with all these transactions that give them the highest fees, and they find the winning block, and they just found the winning block. So now they're working on the next block before the network is even cognizant that a new block has been found, but they get very lucky very quickly. So quickly, they didn't actually even have time to bring in a new set of transactions for a block. So the short answer is that miners are economically incentivized to include transactions with the highest fees. So, okay, so about Bitcoin being transferred. Bitcoin is transferred in transactions. It's just how Bitcoin ownership changes hands. So transactions are fairly simple. They take a set of input UTXOs and the arguments to the redeem scripts, and they create a new set of UTXOs such that no new Bitcoin is created. Any difference between the sum of input UTXO values and output UTXO values is the transaction fee which is given to a miner. And I mentioned here, higher transaction fee is more incentive for miners to include your transaction in a block. Transactions are typically signed by a private key, so they can't be tampered between the point that they are broadcast to the network and when they're included in a block by a miner. And broadcast transactions are gossiped by the network, so everyone receives copies. One interesting thing about transactions is because these nodes are all gossiping these transactions, there's actually no single authoritative set of transactions. Instead, each node has its own set of transactions, which largely overlaps with other nodes in the network. So this set of transactions that each node has that are not yet confirmed by the network, they're said to exist in the mempool, and the transactions are naturally considered unconfirmed. So here's a diagrammatic example of these transactions and these input UTXOs being converted into output UTXOs. It's fairly straightforward. Every single unspent transaction output can be an input for some transaction. And every transaction is going to, well, I guess a transaction doesn't have to generate an output. You could give everything to the miner, I guess, but most of the time, transactions always include outputs. So it's really just a transformation function of one set of UTXOs to a new set of UTXOs. So
Noah, we have a question in the chat.
Okay.
Long is asking, the block ID, the hash, has a lot of leading 0 bits out of 256 bits. Will this limit the range of block IDs? Will 2 blocks have the same ID?
I guess that could be possible if there were enough leading zeros. But if you were to have that many leading zeros, let's think about this. Bitcoin has about 600,000 blocks. So that means that you'll probably have at least sort of 20 bits that they could all sort of collide on. 20 bits is going to be 1,000 times 1,000, which is 1,000,000. So, okay, if we have 20 bits which are non-zero, that means that we are going to have about 230 bits, which are actually going to be 0, which is a lot. So if we were to convert, let's see, 230 bits to, let's say, decimal, let's say 10 bits is 10 to the third. So that means we have, let's see, 23 times 10. So that we would essentially have, okay, 23 times 3, which is 10 to the 69. We would essentially need to have 10 to the 69 hashes to be able to create a block with that many leading zeros, which is a huge amount of hash power. So I haven't actually sort of done sort of more detailed calculation where, I think, okay, what year, assuming that our mining power is increasing at the same rate, at what year are we going to have potential collisions between blocks? But in case that were to ever happen, there would probably be a fairly simple solution. There would probably be an update to the network, which would change the block ID to the hash and the block height, which would sort of reduce the chance for any kind of collision like that. Then you could only have that kind of issue if you had 2 blocks at the same height, which is a much smaller problem. So I don't have a precise answer for when that could be a problem, but it doesn't seem to be a problem yet. And I haven't heard anyone chat about it. So I'm guessing that it won't be a problem for a very long time, if at all.
Noah, when you mentioned the networks, you can change the network. Is the network configurable?
Some parts of it are. So there's this concept of hard forks and soft forks, which are essentially just updates to the network. Are they backwards compatible or not? So one example of a backwards incompatible change is, I think the Bitcoin blockchain timestamp uses like the Unix time, which is gonna essentially run out of digits in the year 2039, in which case there's going to need to be an update to the network then, just because there's gonna be an integer overflow issue. So there are some cases where a hard fork is necessary. It's generally pretty hard on Bitcoin because you have 10,000 nodes. Like, they're all not gonna include, update their software at the same time. So it's probably gonna be pretty painful. Any hard fork is gonna be very painful to do. But it's clear that Bitcoin is going to need at least one hard fork between now and 2039. So at best, they should be used sparingly. The network is upgradable, but the problem is that the nodes that haven't upgraded are potentially going to be on a new network. So that's sort of the issue here. It's sort of a reality of these blockchains in general, where there's no centralized point of coordination, and because of it, the design needs to be very careful to reduce the need for these backwards incompatible changes. So, okay, and I was talking about miners. So Bitcoin miners compete to construct the next valid block for the tip of the blockchain. So on average, blocks are constructed about 10 minutes. There's a huge variance to this. It could be an hour before the network finds a block. It could be seconds. And it's generally not, let's see, what's the standard deviation? It's probably close to 8 minutes is just my guess. And a block is valid if it passes the usual consistency checks, contains the nonce such that the hash of the block meets a special difficulty target. So that means that its hash is very small if you interpret this hash as a decimal number. This difficulty target actually adjusts. It adjusts about once every 2 weeks. Bitcoin goes based off of block time. So it's really 2016 blocks according to the protocol, which is about 2 weeks. So if it took longer than expected to produce the last 216 or 2016 blocks, difficulty lowers. It becomes easier to create blocks, and vice versa. If if the last 2 weeks of blocks was created shorter than it should have been, then the difficulty rises. So in that way, even though we're constantly getting more powerful computing hardware, we went from CPUs to GPUs to FPGAs to ASIC devices, and each of them were probably 10x faster and more efficient than the last generation of devices. Despite that, these difficulty targets adjust such that we're still getting 10-minute block times. So this means that the emission of Bitcoin is pretty constant. And blocks don't actually need to contain transactions, which I mentioned, but miners do include valid transactions, so they get to keep the transaction fees. The intent of this Bitcoin network is that eventually the miners will be funded 100% by transaction fees. So these block rewards that I mentioned are actually just meant to be temporary. So every 4 years, the block rewards decrease by 50%. The initial block rewards were 50 Bitcoin per block. And currently it's 6.25 BTC per block. And in about 3 years, actually about 3 years and 2 months, it's going to be 1/2 of that. So, 3.125. Eventually this reward will approach zero. It'll probably hit exactly zero because computers don't have infinite precision. It'll reach exactly zero in about 2140. But long before then, the rewards should be insignificant compared to transaction fees. It's a bit of an open question if these transaction fees can sustain the network, because that means that you constantly need transactions to be sent for this network to be extended with blocks. But this is sort of an important design decision of Bitcoin, where if this is possible, this will mean that Bitcoin has a fixed supply cap, which is a fairly big deal in terms of money. So it's really everyone's hope that this works out. And at least so far, it doesn't seem wrong, or at least not obviously wrong. So a little bit about how miners organize. They organize according to pools. So let's say you're a miner. You have an ASIC device. It costs about $8,000. A Bitcoin block reward is about $380,000. So you might think to yourself, okay, this hardware might have to run for many decades, if and longer, to get a single block, but this hardware is probably going to die in several years, or just actually be deprecated because faster devices. So for business reasons, miners want a consistent payout. That's pretty reasonable. So how it works is that you have a mining pool operator. It's like a pretty centralized setup. You've got a mining pool operator. The operator decides on the block template and then sends it to all the pool participants so that they can try various nonces. So everything is decided except the nonce. This is like parallelizing the creation of a single block among many separate mining entities. So then you might ask, okay, how do we know how to reward people for the amount of work they're putting in? Well, it turns out that these pool participants can submit blocks to the pool operator whose nonces result in a hash with many leading zeros, but not good enough to submit to the Bitcoin network. And this proves that they're doing a certain quantifiable amount of work. So that way you can have a great deal of variation among these pool participants and in terms of their hash power, and reward them appropriately. When a block is found, the reward goes to the pool operator because they chose the block anyway. They'd probably just set the Coinbase to go to themselves. And then it's up to the pool operator to distribute the rewards properly to the pool participants, minus whatever their fee happens to be. So here's the distribution of Bitcoin mining according to pools. Pools are very, very popular. And generally the incentive is to mine with a bigger pool because that means a more consistent payout. So Bitcoin has 144 blocks per day. So if you have sort of a share of the network that's smaller than 1 out of 144, so Foundry USA probably doesn't find a block every single day. Maybe it's like half days or most days, but not necessarily every day. But F2 pool probably finds it, well, they have to find it every day. That would be like a statistical, accident for them to not find a block in a single day.
Noah, is there a limit number of transactions included in a single block?
Yes, there is. So Bitcoin has actually changed this over the years, but it's now set at 1 megabyte, and the intent is either not to rise this or to rise it very slowly. So if you have 1 megabyte of transaction data, the average transaction is 250 bytes, and how this works out is Bitcoin can include, the throughput of Bitcoin is essentially 7 transactions per second max. And this is determined by the block time, 10 minutes. And the size of the block, transaction data, a megabyte, and then the size of the average transaction. Turns out there are special kinds of transactions called SegWit, which are sort of like more data compact transactions or sort of data compact addresses that Bitcoin is trying to incentivize by this concept of virtual weight. And what this means is that a block can actually be up to 2.2 megabytes, but this is largely determined by the percentage of SegWit transactions. So if you have 2.2 megabytes and 250 bytes for the average transaction, that probably gives you about 14 transactions per second bandwidth. And the reason for keeping the block size sort of limited and not just increasing it all the time, because it might seem like you could just increase it all the time. You get more throughput, and that means more people can use Bitcoin with lower fees. So why not do it? Well, it turns out that if you have larger blocks, that means that the burden on full nodes is larger. So Bitcoin's blockchain is currently about 360 gigabytes, and naturally it's growing. But if you reach a point where you cannot run a Bitcoin node on commodity hardware, that means there are going to be a lot fewer full nodes. And Bitcoin security is dependent on many things. One of them is the number of full nodes. You want the largest set of full nodes as possible. This sort of ties into this concept of decentralization. So that's sort of the intent on keeping these blocks sort of from not getting too big.
We have another question regarding the poll. How does the master poll node verify workload? Is it possible to hack the poll software so that participants are rewarded for conceptual workload, but actually not done?
So let's see. You're wondering how you can fake the amount of work that you did? Is that sort of the question?
Yeah, I guess the question is, can you hack the pool? Because you mentioned pool is centralized.
Right. So I guess the mining pool operator, you have to trust them. It's, the mining pool operator can almost do whatever they want. There's not, as far as I understand, there's not a way to verify that they're distributing the rewards accurately or anything like that. But the pool participants are going to have a hard time faking the amount of work that they're doing, because the mining pool operator decides on the block. So it's not like the pool participant is going to know in advance what this block they need to mine on is going to look like. And it's not like they have a way of pre-computing it or anything like that. I suppose there could be an issue where, for example, if you were sort of, let's say, if you were a man in the middle, you had a way of sort of intercepting the traffic of other pool participants, where you see the blocks they're trying to submit and you try and front run them and submit under your name. That could be a way of cheating it. So I imagine that these pools, sort of encrypting your communication between the participant and the pool operator is probably pretty important. And I suppose, there are a lot of different ways you can conceptualize possibly an attack where someone hacks the mining pool operator's software and maybe just relabels a fraction of these incoming blocks that are not good enough to submit to the network as belonging to them. So I imagine that there are a few ways that you could probably go about hacking this if you had the capabilities to do so. Okay, so we're going to jump into what are we even using Bitcoin for? We spent all this time talking about what Bitcoin is. So the first place to start are features. So Bitcoin does a lot of things that are just very unusual for assets of any other kind. The first of which is censorship resistance. These transactions can't be censored or blocked by anyone. Compare this to PayPal. A government can shut down PayPal. But shutting down Bitcoin is a bit harder because that would largely mean shutting down all of these Bitcoin nodes, all 10,000 of them across 193 jurisdictions. Killing network seems to be a bit infeasible. There have been motivations to do so. Governments have generally made it very illegal to start a private currency like e-gold or the Liberty dollar, but they haven't been able to stop Bitcoin. Now, only one copy of that blockchain needs to survive. So Bitcoin could survive a nuclear war, which is pretty interesting. There's robust client-side verification. So counterfeit gold and dollars are common. So gold, for example, there are ways to verify it with like a higher degree of rigor. Like you would have to flatten a gold bar, then you would have to take an X-ray spectrometer and scan it, and then you'd probably want some way to like return the gold to some other useful form. But there's no real concept of counterfeit Bitcoin. The closest you could possibly get to counterfeit Bitcoin is if you had your Bitcoin on an exchange and the exchange sort of lied to you. Maybe the exchange was insolvent and said, oh yeah, we have your Bitcoin, but they don't. That's the closest thing you get. But if you run a full node, there's really no concept of that. There's also this public auditability. No one really knows how much gold there is in the world. There are estimates on sort of the gold mined over various years, and I guess if you sum it all up, maybe all the different approaches sort of converge within a certain range of values. But Bitcoin, you can know the exact number of Bitcoins that exist out there within a fraction of a second. You really actually just run one command on your Bitcoin full node. It counts all the coins and all the UTXOs. Verifying the supply of US dollars is similarly complicated. No one really knows the full answer. There are estimates, but the client-side verification is not really there for you to do so. It's a bit messy, it involves trust. There's also this concept of permissionlessness. You can set up a Bitcoin address no matter where you live. Your government could be non-functioning. You could be anywhere in the world, or possibly not, even on another planet technically. You don't need a social security number. You don't need to go through know your customer regulations or any money laundering laws. And because of this, no one can deplatform you. Bitcoin truly is for everyone. This concept of immutability is also interesting, where no one can change accounts or balances because it's computationally infeasible. But PayPal can sort of nominally change a balance. A bank can. In fact, when a central bank creates money, all they're really doing is changing a number in a database. There's also this inelastic supply cap. If the price of gold goes up, gold mining is going to accelerate. But if the price of Bitcoin goes up, Bitcoin can be mined a little bit faster because let's say it becomes more profitable to mine, so you turn on some old ASIC devices. But after 2 weeks, you're gonna have a difficulty adjustment. So on average, Bitcoin's emission is constant. It's an inelastic supply cap.
We have a question. What is the message being transmitted between a master and the participant?
When you say master, what does that mean? Because Bitcoin doesn't have a concept of master something. So are we talking about users and nodes or miners, or which entities are we really talking about?
Zijen, do you want to speak up to explain your question, or you can type it in the chat?
Yeah. So my question is the message in the mining pool. So the master is like sending out assignments for participants to mine. So what's the return message? Is it like ID task, something that they work or not, or some other messages?
Well, I don't know the details of Bitcoin mining. Haven't really been involved in that. So I don't know exactly sort of how the protocol works as far as communication between pool operator and pool participants.
Yeah. So this question is related to the former one, because if the answer is just simply yes or no, it's like success or failure, then I can just answer all failure without any computation, and I could be largely correct.
Right. So let's see. to prove that you did some work, you have to submit nonces such that there is some provable amount of work done. So if you don't submit any nonces that correspond to a fairly low hash, then it's not really, it's sort of assumed that you're not doing any work. Okay, so I guess I'll chat a bit more about what you can do with Bitcoin.
Yep.
So I talked about some features of Bitcoin, but now this is sort of where the real world comes into play. My favorite example is the concept of you being in 1940s Germany and you trying to flee your country. Now, countries typically have capital controls, especially countries in distress, especially. So what this means is that if you're in an airport, you'll be searched. If you're at a checkpoint, you'll be searched. If you have gold, cash, jewelry, etc., it will very easily be confiscated. But with Bitcoin, you can carry arbitrary amounts of wealth in your head. All you have to do is memorize the private key, and no one is even going to know that you control Bitcoin. So you can flee with your wealth like that, and that's pretty incredible. You can also protect yourself from hyperinflation. So let's say you're in Argentina, Venezuela, you essentially might want to put your money in something with a fixed supply. Now, dollars are typically used for this because dollars are actually pretty liquid. Bitcoin is also an option, and it might be an option that you would consider because capital controls often are also designed to prevent, let's say, people from using dollars, for example. So Bitcoin's permissionlessness and openness sort of makes it at least a candidate to consider. So you can also protect yourself from government financial censorship. So if you're WikiLeaks, if you're an organization that your government just doesn't like for political reasons or any kind of reason, no one can shut down a Bitcoin balance. You can send money to anyone in the world from anywhere in the world at the speed of information, which is essentially close to the speed of light. So that's pretty interesting. You have multi-signature addresses which have no analog and physical assets. So I mentioned Bitcoin's programmability. One of these is being able to send funds when N of M signers approve the transaction. And this is done without sort of any trust. You don't, if you were to try and do this today, you'd probably involve a bank of some form, so a third party that's trusted. You can do things like store wealth without the need for physical protection. If you own $1 billion in gold, you need a big vault. If you own $1 billion in Bitcoin, well, you could memorize a private key. It could be on a USB. You can store arbitrary amounts, in essentially extremely tiny spaces. It's programmable, as I mentioned. And it's an alternative to an overly complicated, overly regulated financial system. So Bitcoin has had a bunch of different narratives as to what it is for. Naturally, it's sort of an emerging technology. It has a number of different uses, and there's sort of a number of different explanations that have come up. The first, which is fairly obvious, is the eCash proof of concept. When Bitcoin was started, it was largely considered a toy project. No one really knew if it would work. There were many, in fact, no one really expected it to survive for very long, and that was a fairly reasonable assessment. Just too many unknowns, and it's too young. But as Bitcoin survived over the years and didn't die, people started to view it more as a production system. The next big narrative was this concept of a cheap payments network. So Bitcoin block rewards were very high. The number of users was not very high, which meant that people could easily get their transactions included in blocks because there were probably fewer transactions than there was block space. So no one had to compete against each other. So the transaction fees were essentially fractions of a penny. And that's one way of viewing Bitcoin as a very cheap payments network. But as Bitcoin became more popular and more people sort of onboarded, and we reached these sort of limits to how much data you could include in a block while still allowing these full nodes to run on commodity hardware, then these transaction fees started to rise. There was competition to get your transaction included in a block, and this no longer became cheap anymore. Today, Bitcoin blockchain transaction probably going to cost you $8. Could be more if there's congestion in the network, like if some major company says, oh, we added Bitcoin to our balance sheet. There's going to be a lot of trading on the network, and essentially those fees will rise at least temporarily. It was used a lot for for darknets, the concept of combining Tor, which was essentially a hard to censor website, with Bitcoin, which is a hard to censor payments network, allowed you to create essentially a censorship resistant e-commerce store, the whole concept of a darknet market. And that narrative kind of faded in part because Bitcoin is very public. It is not really a secret who is sending money to who with what balances, even though Bitcoin's pseudonymous. So, you know, you don't necessarily know the full identity of someone, but you can still get an address. So for example, if you do something, you have some sort of illicit transaction that's traced on the blockchain, and then you take that money and you deposit it to your Coinbase account, someone could infer that your identity if they subpoena Coinbase. And the most popular narrative today is this concept of a censorship resistant e-gold. So I chat about that right here, Bitcoin versus gold. Bitcoin is an improvement on gold in a number of ways. The first is verifiability. I mentioned that the concept of counterfeit Bitcoin is not really a real thing, but counterfeit gold is very common. To actually verify it, you'll need to flatten it. You'll need to use a spectrometer, which costs thousands of dollars. It's not really feasible. Bitcoin can be divided into much smaller units than gold in a practical way. So even though the smallest unit of gold is an atom, it's not really, you know, reasonable to sort of count atoms, but it is easy to sort of set Bitcoin at sort of arbitrary levels of precision. There's better portability. Send Bitcoin anywhere in the world for a transaction fee and wait an hour just for these blocks to confirm so your transaction doesn't get orphaned or reversed or whatever. For gold, you have to mail it, you have to pay for insurance, you have to wait weeks. As far as custody, I mentioned that Bitcoin, you can store arbitrary amounts of value in your head if you care to. Scarcity. Bitcoin has a fixed supply cap of 21 million units. This is set by the protocol. Gold is historically inflated at about 1.8% per year, and this means that after about 35 years, you're going to lose half of your purchasing power in gold. Another concept is Bitcoin is an uncorrelated asset. So portfolio managers are always looking for ways to reduce their portfolio risk while also maximizing their upside. So they typically try to find uncorrelated assets such that all their assets won't go down at the same time. So Bitcoin's average annualized performance is 230% per year. Some years Bitcoin can go down 85% or more, but on average, Bitcoin seems to go up. So if you have a small allocation to Bitcoin, like 1 to 5%, your downside is fairly limited. Your upside is going to be pretty good as long as this performance sort of increases even in the near term. So another concept is Bitcoin is a reserve currency for crypto. There have been so many different cryptocurrencies that have been created with different design decisions, different sides of a given trade-off. And for a long time, it really wasn't clear if Bitcoin would be replaced by a better technology. Now, on the right is a chart of Bitcoin's performance, and each of these squiggly lines is another cryptocurrency, and it's priced relative to Bitcoin from the date that it was launched to, I guess, you know, the present day, and different coins have different ages. And it seems like Bitcoin has really held its place. So it probably speaks to the importance of its use cases, the sort of the wisdom of its design. And here's another chart about the overall market capitalization of Bitcoin versus other crypto assets. All of these, the total value of all these cryptocurrencies is going up, but Bitcoin seems to have mostly held its own as the dominant cryptocurrency, even for 10 years. Okay, so this is sort of a good stopping point. We are almost exactly at the 1 hour mark. And if there was one other topic I would have talked about, it's Bitcoin scalability. It's how is Bitcoin going to scale beyond 7 transactions per second? Because that's clearly not enough for sort of adoption by billions of people. And that will end up being done with state channels. I'm not going to go over it now because I think it's probably a good opportunity to start questions and answers. And the intent of this presentation was to be an hour anyway. But I will provide these slides so that you guys can take a look at it if you care to. And I also include a number of very cool resources at the end. each of these are sort of really great reads. So I'm not just throwing a bunch of links together. You're going to love them. So, okay, I'm going to give the floor to you guys to ask questions.
Thanks, Noah. Any other questions? I have a question about the hashing. You probably know this. No, the quantum computer can break the hash really easily. And do you think the advent of quantum computing can break the Bitcoin system?
So the security of Bitcoin depends on something called the discrete logarithm problem. It's sort of a basis for, I think, the elliptic curve cryptography, which is a public key cryptography Bitcoin has. So if quantum computing came out and was able to break the discrete logarithm problem, then yes, it would be a very serious problem, not just for Bitcoin, but for anything that is secured by modern cryptography. So yes, it would be a disaster, but at least from what I've heard, it doesn't seem like we are truly anywhere near this threat being in the next 5 or 10 years. Maybe that will change, but it has sort of been a concern that that has been mentioned, but that at least people whose job it is to pay very, very close attention to Bitcoin do not seem concerned about in the near or medium term.
Got it. And I have another question for the transaction. How does the transaction fee being determined or advertised?
So each transaction has a set of input UTXOs and a set of output UTXOs. So if you take the sum of the inputs and you subtract the sum of the outputs, this number has to be at least 0. It can be greater than 0. If this number is greater than 0, that difference is given to miners as the transaction fee. So it's not explicitly set, it's sort of implied.
Got it. Thanks.
I have a question following the question Mosaka just asked. As you just explained, the tips the miner can get decrease every 4 years. So when the tips approaching 0, then people still provide machines to work as a miner since there is no profit.
So there are 2 ways that you are economically incentivized as a miner. The first is with block rewards, the second transaction fees. Today, the ratio of block rewards to transaction fees is probably close to 10-to-1. So it seems right now that still block rewards are the main economic incentive to be a miner. The intent of the Bitcoin network, and when I say intent, I don't have a proof that it's going to work out this way. It's just that having a hard fixed supply is considered such an incredible feature that if this can work out, that's the direction that it's going to go. So it's sort of an open question. We are going to find the answer to that over time. It seems like it really depends on people using Bitcoin. These fee markets for trying to get your transaction included into a block need to be more competitive. And that's it's not the main reason why block size is capped, but it's probably an important reason for it. Although you could also argue that if your blocks are larger, then that means there are more transactions and you can include more transaction fees. But I guess the short answer is nobody actually knows if in 10, 20 years, when the block rewards just become insignificant, and it's also, at some point, Bitcoin can't go up forever. At some point, the fiat value, the dollar value of those block rewards is going to start to go down in block reward terms. So at that point, I guess we're going to find out.
Got you. Thank you.
How do you value Bitcoin? How is the price of a Bitcoin determined?
Sure. The very short and obvious answer is supply and demand. But if we're to get a better answer, maybe another way of thinking about this is Bitcoin is a huge improvement on gold. To say it's a 10x improvement probably doesn't even do justice to Bitcoin. Gold's market cap is currently about $10 trillion. Bitcoin's market cap is about $1 trillion. If you think about the history of what happens with digitization, so for example, take Amazon, or at least the original Amazon when it was just an online bookstore versus a physical bookstore, or take the concept of CDs and DVDs to these sort of paper records, or Uber to taxis. When you have a new solution that is just such a better fit that it sort of disrupts the old solution, typically it doesn't just capture the old market cap, it grows much larger. So for example, I think Uber today is more than 4 times larger than the entire taxi industry. And Uber is just one ride hailing company, the largest one, but still just one. So if you think about it in those terms, then one way of looking at Bitcoin is that its main competitor is gold. And that would mean that Bitcoin's market cap could realistically reach 10 trillion or more than 10 trillion if there are greater uses of gold. Today, I don't care to use gold, but I would care to use Bitcoin. You can almost think of Bitcoin as an insurance policy in a way that gold might not be. And if you want to go even further than this, I mean, this is all speculation, so sort of make your own choices on this. But if you think about good ways of representing value, money is an information system. What's really important is scarcity, that you can't sort of inflate the supply just due to demand, like for example, seashells don't make good money. So the total value of land is about 200 trillion. If you want to compare Bitcoin to land in terms of a monetary premium, and when I say monetary premium, I mean the value beyond its actual inherent utility. Gold's monetary premium is, I think, about what, like 9 to 1. Like Bitcoin's gold's industrial use doesn't actually justify gold's price as a monetary premium due to its scarcity. So if you think about other scarce objects, one are national currencies, and the market cap of that might be around 20 trillion. Land is sort of the real big target. If you think of Bitcoin compared to land in terms of sort of managing scarcity, well, the thing is, you can't actually own land in arbitrary quantities. If you generally own land, you have to sort of buy, you can't just buy like this tiny strip of land. You generally have to buy certain, areas. You also can't own, square or, cubic millimeters of land, but you can own individual Satoshis of Bitcoin. Land is also a lot less fungible than Bitcoin. It's also much harder to sell land. You need to involve lawyers. The actual boundaries of land can be greatly disputed. If you think of sort of land as sort of managing scarcity, there are a lot of aspects to this that kind of make it a nightmare. So what I suspect may be the case is that Bitcoin saps monetary premium from sort of inferior monetary assets. And this will include gold, this will include national currencies, this will include land. I couldn't actually tell you exactly what the monetary premium on land is. At least the last time I tried to find it, I couldn't. But there's a lot of monetary premium to be sucked up. So right now, Bitcoin's market cap of 1 trillion, I could realistically see it growing.
Thanks. Does anyone else have a question?
Hi, Noah. I'm interested in to see the actual content within one blog. I mean, I have went to a website which has like the decrypted contents, and there could be very interesting contents. But I mean, in the designer's view, what are the contents in there, and is it just the intention is it just to record a standard formatted transactions, or does it accept anything else?
So blocks do include standard formatted transactions, but what you can do in the script is you can actually include arbitrary data if you care to. So you can actually use Bitcoin for some very primitive storage. Like for example, if you wanted to put a marriage proposal on Bitcoin to, impress your fiance. I know that mining pools are able to include a small message in their own block, so they typically include the name of their mining pool. That's how we know that certain blocks were made by a given mining pool. So that's one sort of special use of Bitcoin transactions, although the main intent is for Bitcoin to be used as money. And fortunately, using Bitcoin as money sort of has the highest value per transaction. So if that weren't the case, you might have some sort of competing use case on Bitcoin. As far as the actual structure of a block, if you want to actually examine the blocks themselves, there's trying to think of what folder. It exists in a specific folder when you run the Bitcoin software. It's this data is usually labeled BLK, and then it's some fixed length number. So it might be like several zeros and then like this number of the block and then called .dat. I don't know the specific, trying to think of the right name for it, sort of formula for how the data should exist. Like the first 8 bytes should be this in low endian order, or the next 8 bytes should be that. So I don't know the actual data format of a block, unfortunately.
I think there is a website called Blockchain Explorer, and it shows all the transactions, the blocks.
Right. Didn't you allude to that though, that you already knew that that existed? And
yeah.
Right.
Cool.
Noah, do you see, excuse me, do you see smart contracts are much more valuable than Bitcoin?
So the thing about, this is sort of a conversation about Ethereum. For people not familiar, Ethereum has Turing complete transactions. So there's a greater level of expressibility. Ethereum chooses a few different design decisions. They're still trying to be the most decentralized smart contract platform, but some of their design decisions are a bit different than Bitcoin. So for example, Bitcoin's expressiveness is reduced for security reasons. And in Ethereum's case, the expressiveness is an important feature. Another is Ethereum is also changing their consensus layer. So they're changing from proof of work to something called proof of stake. They're also doing something called sharding, so having multiple different blockchains. But the sort of bigger picture here is that Ethereum is a completely different design. So it's sort of hard to compare Ethereum to Bitcoin here, but my take on this is that one of the highest value applications among cryptocurrencies is money. It is a very recent phenomena where there is this concept of a private money, a money that's not sort of determined by scarcity in nature like gold, and also money that's not, whose scarcity isn't determined by a government. So Bitcoin is largely designed to maximize its security and maximize its decentralization. I think those are probably the right design choices as far as money goes. Ethereum is trying to do a little more than that at once. So they are, to an extent, compromising on their design decisions. So for example, one of these design decisions you can think of, and this is sort of a community ethos thing, is there was an event called the DAO in Ethereum, where there was a very big hack of a smart contract. It was a huge hack at the time. And the community decided to change the state of the blockchain with a hard fork, a protocol change, to undo what happened under valid rules in Ethereum. And so this concept of immutability usually is from the context of a single attacker. But you also have to consider the concept of the community collectively agreeing to change the state of the blockchain, which is pretty important when it comes to something like money. So I suspect that Bitcoin's going to hold its own. Ethereum is going to find a lot of value in compute and smart contracting. It's going to be used as money, but I suspect that Ethereum is not going to be sort of considered the most secure option to store wealth. This is just conjecture. I could be wrong. There are reasons to think that Ethereum could outcompete Bitcoin in some way because it is more featureful and it does consider many of the same design decisions as Bitcoin, at least, pre-consensus layer change. So I don't really have the answers here. I think it's a great project, and I think there's a lot of room for many different crypto assets to flourish.
Thanks. If no one has a question, I will continue
Okay.
with another one. Sorry. So it seems like the private key is all you need to have all your transactions. But if you lose your private key, that means you lost all your money in Bitcoin. Is that correct?
Yes. If you lose the secret data necessary to sort of unlocking that redeem script, your money's gone, unfortunately.
And it seems like, human beings are not great at memory, so they forget things all the time.
Well,
and by this,
one interesting thing is, so Bitcoin's expressibility is sort of much greater than you might expect. There are also new sort of protocol, new computing, I'm trying to think of the right word for that, computing features, or let me explain it this way. You could have a Bitcoin script that says this private key can spend the money. However, after a certain block height, another private key can spend the money, and you can give that second private key to your kids. And that can be perhaps your inheritance plan, that if anything happens to you, your kids will have the key. Or you could do multi-signature. So how it might work is you have a 2 out of 3 signers. You might have one of the keys generated by a trusted third party, 2 of the keys managed by you. And you might give one of the private keys to your benefactor, your son, whoever you want to inherit your Bitcoin. If anything happens to you, your benefactor will be able to take that key and also go to that trusted third party and through a legal mechanism, get them to sign off on a transaction transferring the Bitcoin to your benefactor. So there are a few options to approach this. I imagine multi-signature is probably one of the more popular solutions at this time.
Got it. Do we have any other questions? All right, it seems like we don't. Thank you very much, Noah, for sharing information about Bitcoin.
Cool. Thank you for having me.
And thanks everyone for joining. And next week, we'll continue our journey on MIT 6.824, and we will see you on Saturday. Thanks. Bye.